call the oxidant. Now dichromate is a really strong oxidant, so it is always reduced. Okay, and whoever's with dichromate or permanganate gets oxidised. Believe you me, very strong oxidants. Okay, and the last thing we have to do is our justification. Our justification is why we think this and why we think that. Now for your justification you can use, so for oxidation, the thing that's been oxidised, or the reductant, or reduced, whatever's been reduced is known as the oxidant because it's done it to the other thing. Okay, it's done it to that and it's done it to that. Okay, you can use, so if something's, it's lost electrons or gained electrons, you can say if it's been oxidised it's gained oxygen as your, or lost O, or you can say it's lost hydrogen or gained hydrogen for reduced. Okay, so whatever was placed in front of you, these are ways that you can justify whether something's been oxidised or reduced, or whether it's the oxidant or reductant. Remember, the oxidant or reductant are the other way around because it's doing it to the other thing, and that people get caught up on that. And it's an easy mistake to make. Oh, it's been oxidised, therefore it's the oxidant. No. If it's been oxidised, it's caused something else to be reduced, so it's the reductant. So once you've got through that, so you can use any of these. If you want a nice fat excellence grade, and I'm kind of thinking that probably a lot of you do, you've got to just justify it with this. So if something's been oxidised, the oxidation number has gone up. Or if it's been reduced, the oxidation number has gone down. So if we look, say, at iron 3+, no, we won't look at that yet because you don't know the rules. So oxidation number rules. Oxidation number rules. So on your book on page 58, you've got the oxidation number rules. You can just link that page to your notes. You can say in your notes, see page 58, or you could 59 or whatever it is. Or you could just copy them down when I write them. It's up to you, I don't care, as long as you are able to understand what the oxidation number, how you work out the oxidation number of any species. Okay? So we use it for our justification. So dichromate has been, the chromium atom in dichromate has been reduced because its oxidation number has gone down from this to that. Okay? So then you can actually justify it and you'll know that you're absolutely correct. Okay. Alright, so 1. Atoms have an oxidation number of 0. So here's an example. The hydrogens in this molecule have an oxidation number of 0, and I just stick it above them. Okay? An iron atom has an oxidation number of 0. Get the whole idea? So if it's an atom, it's not an ion, it's not a compound, it's just an atom might be hanging in a molecule with another atom of it the same, or it might be just hanging by itself in a metal lattice. Doesn't matter. If it's an atom, it's got an oxidation number of 0. So if it's become an ion, you know the oxidation number is going to go up or down. So 2. 2 is a bit of a big rule. The first bit's easy, the second bit's a little bit more difficult. Ions, their oxidation number, can I just use ox.no now? I'll just put ox.no. Is that alright? Because it gets awful when you have to write oxidation number about 100 million times. So you can do it on your page, write it once and then put the abbreviation beside it, and then you can use ox.no. Okay? Ions, their ox.no is the same as their charge. Okay, so say we've got iron becoming the iron 2 plus iron. Okay, let's set with this scenario. We know iron as an atom has an oxidation number of 0, but the iron's oxidation number is going to be 2. So the oxidation number has gone up, therefore this has been oxidized. You always talk about the species you started with. Okay, so Fe has been oxidized as its ox.no has gone up from 0 to 2. So that's how we write a justification. We say, and we always talk about the species we started with. We don't try and do the reverse or anything like that. Because we're talking about what's happened in our reaction. Well, what we started with is turned into something else. So what we started with has been oxidized. Let's look at the other justifications we could use. So iron has been oxidized, so it is the reductant. Has it lost electrons? Yes. Has it gained oxygen? Can't use that one. Lost hydrogen? Can't use that one. But we can use oxidation numbers gone up as well. So we'll just put it has lost electrons. It has lost electrons. Therefore, it is the reductant. We have to get our statement all the way down to that word. So we use oxidise and reductant in the same justification to show that we understand the terms. Okay. Alright. We all happy with that? Fabulous. Okay, 2, that was 2, 1. 2, 2. Polyatomic ions. The ox.nos of the species contained in the iron is equal to the charge of the iron. So let's write permanganate and dichromate and see what we mean. NNO4 minus. So I'm just using a bit of algebra to go through the logic, and this is where you realise that algebra actually is quite important, okay, to work out what we don't know. So the oxidation number of magnesium we'll call A. The oxidation number of oxygen we'll call B, but we've got 4 of them, okay? So we've got the oxidation number of manganese, did I say magnesium? What an idiot. The oxidation number of manganese and the 4 lots of the oxidation number of oxygen is equal to -1. Okay.
Wait, what?
Who's saying a what?
Wait, I'm confused.
Okay. What I'm saying is the oxidation numbers of these guys have to add up to -1 because that's the charge on the iron. Okay? So I know I've got 1 manganese atom, its oxidation number I'm calling A because I don't know what it is. Alright? We use letters in maths and we don't know what they are. We don't know what the number is. And I know whatever the oxidation number of oxygen, each oxygen atom in here, I know I've got 4 of them. So I know that A plus 4B must equal -1. The oxidation number of manganese and 4 lots of the oxidation number of oxygen has got to equal -1. Let's do dichromate now. Cr2O72 minus. I'll put it underneath. Oh, I'll put it above because that's normally what we do. So 2 oxidation number of the chromium atom plus 7B, B is the oxidation number of oxygen, is equal to -2. So 2 lots of something and 7 lots of something all has to equal -2 because that's their oxidation numbers. Remember, we've got to think of each atom separately. Just because there's 7 oxygens doesn't mean they have to divide up the value of the oxidation number. They've each got it. Okay? Alright. Ready for rule 3. Rule 3, I think, can you just check in your books because I'm going from memory, is that oxygen always has an oxidation number of -2 except in peroxide where it's -1. Have I got the right rule? What's 3?
In compounds.
Ah, yeah. Species and compounds add up to 0. The ox.nos of the species contained in a compound add up to 0. Okay, so let's write carbon dioxide, something we're all familiar with. There's carbon dioxide. And so carbon, we've got whatever the oxidation number of carbon and whatever the oxidation number of oxygen, and I've got 2 of them, have to equal 0. All happy with that? Because it hasn't got a charge, it's got a charge of nothing. So it's kind of like the other rules. You've got a charge of nothing, your oxidation numbers add up to that charge, which is nothing. Okay? 4 and 5 are quite cool because they help us work everything out. And I love rule 4 and 5. Personally, they're my favourites. Rule 4 is oxygen always, I love it when we say always in chemistry because then we're going to make an exception. Oxygen always has an ox.no of -2 except in peroxide, because we deal with peroxide, so we've got to remember this, where it's -1. Okay? So when you deal with peroxide, H2O2, you've got to think, no, that oxygen, that's going to be -1 because it's peroxide. Everything else, it's 2. And lastly but not leastly, hydrogen always has an ox.no of +1. And there's a second part to the rule, but you never use hydride. So, in a hydride ion, do you know what a hydride ion is? You know how hydrogen's got like one proton and then it's got an electron around the outside? When it makes a hydrogen ion, H+, it loses that electron. You're all familiar with that. Sometimes, because it only needs to gain one electron to get the shell, in rare circumstances it will form that. And that's the hydride ion. And you don't use it. Alright, but that's what's going on. So that has an oxidation number of -1. That has an oxidation number of +1. And if it's just hydrogen itself sharing an electron with another hydrogen, then it's an oxidation number of 0. So because that first shell only has 2 electrons, hydrogen kind of bats for both teams. Alright, same with metals and non-metals. It has a bet each way. It's a bisexual element, really. Because it goes both ways. Okay. Alright, so let's do some working out now. And so we're going to spend the next few minutes working out some examples of ox.nos or oxidation numbers. So let's have a look at the chromium in dichromate. So ox.no of Cr in dichromate. And we're going to look at dichromate turning into the chromium ion. And we're going to justify the fact we think that dichromate has been reduced and therefore it's the oxidant. Okay, let's have a look. We know that 2A, let's do it underneath now. 2A plus 7B equals -2. Is everyone alright with that? 2 lots of the oxidation number of this plus 7 lots of the oxidation number of this all must equal the charge of the ion. Are you happy with that? Let's start putting in some numbers. We now know what oxygen is, don't we? So 2A plus 7 lots of -2, because oxygen's oxidation number is -2. So 7 lots of -2 is what? -14 equals -2. Okay, so we'll take the -14 over the magical equals bridge. Did your maths teacher teach you that? Or was it change the side, change the sign? Change the sign. So the 14, I always say we're going to take 14 away from each side. We're going to add 14 to each side. So if I take away that -14, I'm really adding 14 to get 0. So I've got to do the same to the other side. So 2A equals -2 plus 14. So 2A equals 12. So what's A? What's the oxidation number of chromium? 6. I'll put that up. So I use that terrible thing that people say there is no use for to work out a chemical problem. And that's where, trying to say this to a year 10 who's struggling over algebra, they say, what do I need this for? Well, actually, from now on, we think through all of our problems using algebra. It helps us get our thoughts down in a clear, concise way. So next time you feel like saying to your maths teacher, what are we going to use this for? You now know the answer to that. Chemistry. And when we start doing, you guys start doing calculus yet? Differentiation, that sort of hoo-ha? Not yet. Oh, wait till you get to that. All right. But I haven't finished the problem because I've got to work it out here. I've got 2 chromium ions. If one of them, what is the charge on each chromium ion? So this is actually this, isn't it? Is that right? That's short. That's like algebra 2. Funny. Okay, so what's the charge on this? 3 plus. Okay, so I can write my justification now, because I know the charge on each of these was positive 6. The charge on this, the oxidation numbers of this was positive 6. The oxidation number of this is positive 3. Notice how that's harder to work out than this one. So we know that the chromium atom in dichromate, or each chromium atom you could say, you don't have to, has been reduced because its ox.no has to positive 3. It has also lost oxygen. Okay. Electrons aren't really, because you don't know the electrons came off the chromium, so we won't talk about the electrons. It has also lost oxygen, therefore it is the oxidant. So let's just pick apart this statement. I'll put it up here. Let's just pick apart this statement. This is about as hard as it gets. Alright? Because usually with dichromate you have an iron 2 plus going to an iron 3 plus, and they're really easy to do oxidation numbers on. Okay. But in a dichromate reaction, just remember positive 6 to positive 3 if you can. With the dichromate, that's what it does. So it doesn't change in any reaction. That when you've got dichromate, that's always the situation. Just like the equation is always the same. Okay, so I've talked about the species, and I'm talking about the species Cr, or chromium. Because polyatomic ions are groups of atoms bonded together covalently, sharing electrons, but they've all acted like a mob and stolen a couple of electrons. So they have more negatives than they have positives collectively. So the Cr in dichromate has been reduced because its oxidation number has lowered from positive 6 to positive 3. Notice I've quoted the numbers. It has also lost oxygen. That's another thing. That's another criteria for being reduced, is you lose oxygen. Opposite to oxidation, where you get oxygen. So if it's appropriate, you can also use another justification. It has also, therefore, it is the oxidant. Notice what I've used in my statement. Highlight these things. Highlight the Cr. I've named the species, and I've named the ion. So not just the Cr has been reduced, the Cr in Cr2O72- has been reduced.